All right, this is the last part of section 2.2. We're going to talk about the actual objects of lines. If I write a linear equation with x and y in it, this lets us plot a line in the Cartesian plane. Just like I did when I did y equals 2x plus 1 in the previous lecture. This form, like y equals 2x plus 1, what I want you to notice is that 2 turns out to be the slope of the line, because every time x goes up by 1, y goes up by 2, because the x gets multiplied by 2 before it goes into y. So that 2 right there is the slope, and this one right here, this is the y-intercept. How do I know? Well, the y-intercept is this point right here. It's wherever x is 0, and when x is 0, the only thing left for y is 2 times 0. That's nothing, plus 1. So this 1 is the y-intercept. For that reason, whenever I have an equation that looks like this, y equals mx plus b, m and b are going to be parameters. They stand for numbers here. M is the slope, and b is the intercept. So we call this, well, not very creative, is it? Slope-intercept form. All right, so m is the slope and b is the y-intercept. Oops. And remember, slope is rise over run. So for example, on this line, y equals 2x plus 1. If I go, I have this point 1, 3. I have 2, 5. I have 3, 7. I have 0, 1. So if I go from 0, 1 to 1, 3, I went 1 to the right and 2 up. So that's a run of 1 to the right and a rise of 2. So the slope is 2. Or if I went from 1, 3 to 3, 7, I went 2 to the right and up. 7 minus 3 is 4. So I could also say it's 4 over 2. Well, that's also 2. So it's a different rise and a different run, but the ratio is the same. For every 1 run you do, you're going to get 2 rise. The slope of a line is the same everywhere you look on the line. Doesn't matter which points you measure it from. Let's take a look at how slope looks. Since it's rise over run, larger numbers mean there's more rise for your run. So larger numbers are steeper. For example, here's a slope of 2. I'm always going to use the letter m for slope, just for consistency. And here's a slope of 1/2. Every time we run 1 over, we only rise a half. So it's a lot shallower. If you get your slope all the way down to 0, then no matter how much you run, there can never be any rise. So that's a flat line. Now, on the other hand, if your slope is negative, then as you run to the right, instead of rising, you're going to fall. So here's m is -2, and here's m equals -1/2, steep and shallow, respectively. So here, if I run over 1, I'm going to fall 1/2. Here, if I run over 1, I'm going to fall by 2. So larger numbers are steeper. If it's positive, it goes up and to the right. If it's negative, it goes down and to the right. That's slopes. So I could ask questions about slope like, what is the slope of the line that passes through these 2 points, 3, 4, and 5, 1. First off, let me plot these points and get you a picture of what we're talking about. Here's 3 to the right and 4 up. Here's 5 to the right and 1 up. If I draw 2 points, I can line up my ruler on those points. There's only ever going to be one line that goes through 2 points. We say that 2 points define a line. You need 2 pieces of information to tell what line you're talking about. So the rise from 3-4 to 5-1, the rise is actually -3. We're going to go down from 4 to 1. The run is +2. We go up from 3 to 5. So the slope is rise of -3 over run of 2. So our answer is going to be -3/2. We'll just leave it looking like that. How did I get these 2 distances? Well, it was the change in x and the change in y. So I could write it this way. Slope is rise over run. Or I could write it as how much did the x change? That's the run. Delta x. I use a Greek letter delta, like on a fraternity sign. Greek letter delta means change. You might see that in physics again. So the run is how much x changed from 3 to 5. The rise is how much y changed from 4 to 1. So that's delta y is how I'll call that. Or if you remember when I was talking about the Pythagorean theorem and the distance formula, we could call that rise the difference from the second y to the first y. We could call that run difference from, nope, not y this time, difference from the second x to the first x. So there you go. y2 minus y1 over x2 minus x1. You've probably seen that before. Now there's another form of a line where if you're given a point and a slope, you can use what's called point slope form. Imaginative, I know. Here's how this works, right? Let's say we're given a point x, y. Sorry, let's call the point x1, y1. I'm going to need a little more space here. So that's a point that's definitely on the line. And the rest of the line, well, let's say I know what slope. I definitely know the slope. So any point that goes away in that direction, is going to be on the line. Let's call one of those points x, y. See what we can work out. So I know m, and I know that it's rise over run. So I know it's y minus y1 over x minus x1. All right? Where x and y are our variables for the line, they represent any point on the line. x1, y1 represents the specific point we know. But what I'm going to do is real simple. I'm going to multiply both sides by the denominator. That's going to get this out of the denominator, and it's going to look like m times x minus x1 equals y minus y1. All right, let's take a look at this in practice. In practice is probably a little easier. So if I say, what is the equation of the line with a slope of, how about 4, that passes through, how about the point 1, 3? So I know I go through the point 1 to the right and 3 up. I know that my slope is 4, so I'm going to have 4 rise for every 1 run. That's a very steep line. Let's say some point, so we know m is 4, and I know some other point x, y is on the line, and I want to describe the relationship between x and y. What I'll write is m times x minus the point I'm given equals y minus the point I'm given. So in this case, 4 times x minus 1 equals y minus 3. And that's an equation for the line. You see how that works? Now, if I wanted to write this in slope-intercept form, I could call this my final answer, or I could go a little further. I could get y by itself. I'm going to distribute the 4. So 4x minus 4 equals y minus 3. And then I'm going to add 3 to both sides. So y equals 4x minus 1. I switched the order of the sides just to make it look like before. So y equals 4x minus 1, and I can see from the picture, yeah, the slope really is 4, and the intercept really does look like it's negative 1. So that makes sense. Y equals 4x minus 1. All right. Got a few more pages of notes here. And do a little bit more with lines. I told you that if I know 2 points, then there's only one line that can go through them. So I could ask, what line goes through the points negative 6 comma 4 and 2 comma 0? Now look, it's probably a good idea to draw a picture just to make sure our algebra doesn't go way off from where our intuition of this line should be. So negative 6, 4 is back out here, and 2, 0 is up here. So I'm looking for a shallow negative slope. Maybe it's like negative 1/2 or negative 2/3. I don't know, something like that. But I'm looking for a small negative number, and I'm looking for a small positive number for my y-intercept, you know, right here. So it's really good to have that intuition going into the problem so that if your answer is like wildly wrong, you can notice it immediately. It's called making a ballpark answer. It's real good to always have a ballpark in your mind before you finish solving the problem, just whenever you're doing mathematics. Save you from a lot of headaches. All right, let's see here. Well, I know points, but I don't know the slope. Good news is I can find the slope. It's the change in y divided by the change in x. Well, let's see, what's the change in y? This was, let me label my points. Negative 6, 4, and this is 2, 0. So y goes down from 4 to 0, so delta y is negative 4. And x goes up from negative 6 to 2, so delta x, that change there is 8. Do you see? So my slope is negative 4 divided by 8, which is negative 1/2. Very good. Okay, it's exactly what I guessed. See, it's a negative slope, which means pointing down into the left to the right, and it's 1/2, which means it's pretty shallow. So this matches our intuition from the picture. Now we're looking for a small positive y-intercept. So I have a point and I have a slope, but here's the thing, I have 2 points. Oh geez, which one should I use? Here's the hint, it actually doesn't matter. So my equation y minus y1 equals m times x minus x1. Yeah. I could use this point or I could use that point. I'm going to use both, show you why it don't matter. Let's try the negative 6, 4. So y minus 4 equals negative 1/2 of x minus negative 6. Ooh, that's a doozy. Or if I plug in the other point, I get y minus 0, oh, that's nice, equals negative 1/2 of x minus 2. You know, I think I like this side better. Now, these look like 2 completely different equations is the thing, but let's try putting them in slope-intercept form, why don't we? So if I distribute, I get y minus 4 equals, well, negative 1/2 of x. Now there's 3 minus signs here, so we're going to end up with a negative. Negative 1/2 times negative negative 6 is negative 3. Last thing I need to do is add 4 to both sides. Y equals negative 1/2 x plus 1. Hey, there's that small positive y-intercept I was looking for. It's 1. Let's take a look at this line instead. Well, I'm going to distribute this negative 1/2. I don't have to write that minus 0 because it doesn't change the value. So negative 1/2 x. Now, negative 1/2 times negative 2, the minuses cancel out, and a half cancels out with 2 and leaves us with just a 1. Hey, that's the same equation. So it really is the same no matter which point you used. And that's for every problem, not just this one. It never matters which point you plug in. You're free to use whichever one gives you the easier computation. In this case, I'd definitely pick the one on the right because I don't want to have to multiply 3 minus signs together again. So either way, we get our value. Hey, there's a couple of special lines. If a line is horizontal, I already told you, then the slope is 0. But what if our line is vertical? So the rise is whatever you want it to be. I could rise by 1 or 2 or 5. But the run, so the rise is anything. The run, though, we're never going to go left or right, so the run is always 0. Well, we can't, geez, I misspelled that. We can't divide by 0. Big problem. So the slope does not exist. This is a line that I can't put in point slope form or slope intercept form because the slope don't exist. So the way we're going to write this is, look, all these points have the same x value. Maybe this x value is 4. Then I would write the equation of the line. Don't overthink it. X equals 4. As long as x equals 4, the point's on the line. If x isn't 4, the point's not on the line. So this is the equation of this line. If the line were over here, I could say this is the line x equals -2. It's that easy. That's all we do for vertical lines. They don't come up very often, but when they do, not a lot of trouble. All right, this horizontal line, well, y is always the same. So this might be the line y equals 4. See how easy that is? Horizontal and vertical lines are great. That's all I have to say about them, though. Mathematically, I mean, they're easy. They're not very interesting. Okay. I got a couple of special relationships between lines to tell you about, and then we are done with this chapter. Let's talk about parallel lines. And let's break the video up. I'm worried about this storm taking out power. I want to break this up and make sure I save as much as possible. So, save point here.